Okay, all right. Thank you, Greg, for inviting me to this great meetup. I have been attending this meetup myself long, and thanks for the great talk, Maroon. It's very theoretical and it tells us about the fundamentals of the blockchain in terms of math. And today, my talk is pairing very well that my talk is going to be more on the practical side of how we're scaling the blockchain, how we're improving the scalability of blockchain using off-chain scaling techniques. First a quick disclaimer that I am using a kind of marketing-ish slide, but I will talk on the technical side. Okay. I also inserted some basically technical stuff in there. By the way, let me also introduce myself. My name is Mo. And I work on a project called Celer Network. You can check out our website and also the white paper and Medium post about what we are working on. Okay, so before we talk about scalability in blockchain, let's talk about something else. Let's talk about what is economic activity. Well, one way to look at economic activity is the transfer of information and transfer of value and the exchange or conversion between them, right? Now, if we think about it, over the past 100 years, what happened is that on the information side, we changed from using pigeon delivery network to carry information to using internet, right? So this is like a drastic change that we push the information transfer speed from very discrete event, very slow event, to continuous and speed of light event. But what happened on the value side, let's take a look. So this is already an event 100 years ago. And after 100 years, the same exact bank sit here, right? So it's same exact bank, one from drawing, one from picture. So nothing changed very much. We still have very segregated financial silos. We still have a huge barrier to transfer value. And what's the culprit for that? People know that it's because we still have this kind of trust barrier between different financial institutions, different financial silos. Great, we have blockchain, we have a Bitcoin, we have Ethereum, we have US, we have altcoins. And it enables value transfer between untrusted party with arbitrary contractual logic. It brings us a whole new plane of things we can do and things we can implement. But there's a problem. It's that slow. It's super slow. It's slow like a 1995 cell phone, basically. All right, so, okay, we need scalability right now. We need it right now. But let's calm down and ask this question. What is the end goal for scalability? What is like the target we want to reach finally? Some people say it's a Visa scale, it's 20,000 transactions per second. Some say it's something else. But what is the end goal? How do we calculate that roughly, right? Okay, so maybe one way to think about this is the goal here for the value transfer scalability with contractual logic is to match the scalability of information transfer today. Okay, so what we're talking about for information transfer today, we have 2 million emails sent over the internet per second, 65K Google searches per second, 53 terabyte data per second transferred over the internet. Now, if we do some very rough back on the envelope calculation, let's say we do this kind of thing. Let's assume that for every 1,000 kilobyte of data transferred over the internet, we pair that with the value transfer. It's not to say that we want to bring email to blockchain. It's not that. It's just like we do some rough calculation on the scale, and the conclusion we got is pretty surprising. We need to support something like 530 million transactions per second. Visa is way smaller than this, right? So this should be our goal as the blockchain community. We should shoot for this, not 20,000 transactions per second. Okay, so maybe this is a little bit rough exaggeration, but even if you cut it by 10 times, it's still a very big number. So how do we ever get there? 500 million transactions per second. And what's worse? Let me tell you, worse news here is that transaction per second is actually not everything. Right, so people are so, we kind of have this general fixation on the transaction per second matrix. But another thing that is very important is latency. Right, these two things are very different actually. So if you have, let's say, a 10,000 transaction per second system, it doesn't mean that one transaction will take only like 1 over 10,000 seconds. It could very well be that every transaction still takes 3 seconds, but just on average, it is about 10,000 transactions per second. Now, if you want to have actual user adoption for blockchain technology, we need to achieve the same kind of usability, same kind of user experience as if we're using internet technology, and therefore we need latency instead of only transactions per second. So these are all bad things. Now let's see how Celer can solve all of them. No, I'm kidding. So this is the second part of today's blockchain application stack. You have a blockchain and you build DApps on it. And it's like a web server where the DApps is basically a front end, and you use the blockchain as your database. And you stuff everything on the database, and you query the database, even if the database is slow like a snail. You still do that. Okay? So, but the problem is that blockchain itself is still a work in progress, and even though we have like a lot of scalability, tricks are still being implemented, and techniques, new technology is still being implemented. But in the end of the day, blockchain is still a distributed system. It still requires, even with starting and all these new technology being developed, it is still require global consensus overhead that need to be reached among multiple machines. And we can see that these kind of improvement will have diminishing return in the long run. But we believe that the scalability goal to mass adoption is way above this kind of diminishing returns bounded line. And therefore, we need something new here that is called off-chain scaling. And that will be, we believe, the inflection point for blockchain technology to reach mass adoption. Okay, so how does off-chain work anyway? Right? What do I mean by off-chain? Off-chain means that we bring many transactions from blockchain away from blockchain. Basically, we put it off the blockchain. Now, how the basic concept, including side chains, some names you may heard about like a Plasma in the Ethereum community, and you have maybe you have heard about state channel or payment channel. Let me do a quick poll in the audience. How many of you heard about Lightning Network? Okay, great, almost all of you. How many of you heard about generalized state channel? Okay, great. This is a great audience. Thanks. Okay, so this kind of off-chain technology is fast because there is no large-scale consensus overhead involved. Think about Lightning, basically, and it is secure because you still always have this on-chain bond contract sitting on the chain to ensure that everyone has like bond by whenever like needed, it can be settled to the most recent updated state. But the off-chain word is actually underappreciated now as a layer 2 technology. I don't like the layer 2 name very much because it put a color that is kind of an optimization, right? But we don't think that is optimization. We think the layer 2 or the off-chain word can be a very rich stack in terms of not only technology, which I'm going to talk about what we're doing and what we're working on here, but also on the economic side. That is, off-chain will have its own economic problem to solve and own economic challenges to be resolved. Okay, so let me just talk through like this Celer Network's technology stack, but in the meantime, I will try to be more general and introduce what is the underlying, like what are some of the key concepts of off-chain scaling, and specifically on the state channel side, generalized state channel side. So in the lowest layer of C stack, which is the Celer Network's technology stack, we have cChannel. cChannel supports generalized DApp beyond just a simple payment, and it enables multi-hop state relay. Now, I will just skip this part because most of you guys already know about what is Lightning and what is payment channel probably. Very quickly, what is payment channel is a smart contract where you can deposit money with your counterparty together into this contract, and after the deposit, you can do off-chain transaction because this smart contract is smart enough to take your balance proof that you're passing back and forth with your counterparty to send out like whatever says in the balance proof. There's a challenge process, there's a settlement process, but I'm going to skip that part. So in the end, after all these off-chain transactions, which is does not cost any on-chain consensus overhead, one of the counterparties submits the final state proof to the blockchain, and resolve it. Now, this kind of simple one-hop payment channel can be extended pretty easily to multiple hop by using a technique called hash time lock. But hash time lock, as you will later see, is just a special kind of generalized conditional dependency in our generalized conditional construct. The key point here is that for those who doesn't know, like basically what is a hash time lock, is basically if you have like an Alice and Bob and Carl have like a 3-hop channel, Alice can send payment to Carl without trusting the middleman. That's like what the hash time lock do. But I will skip the actual mechanism here for the sake of saving time. Now, this is a simple payment. Let's talk about another thing that is a little bit more interesting, that is generalized data. That is like you can enable arbitrary state transition or arbitrary program state transition entirely off-chain. Okay, example. Alice and Bob playing a $5 chess game. They're basically betting on each other's chess skill. It's very easy to implement on-chain. It basically looks like this. Alice and Bob shows up, and one of them deploy the chess game contract on the blockchain, just deploy it directly on the blockchain. And both of them put $5 in this contract, in this smart contract, right? And then they start to play. And okay, it's not Alice, sorry. Yeah, but okay. Alice makes the first move. Okay, well, I'm waiting for block confirmation. Okay. I'm really waiting for block confirmation. Okay. Bob can make next move. All right, I won't waste more time. I will just accelerate my block proposer to DPoS. Okay. Okay, now it's much faster. All right, so it's really painful game, and after a while, finally the game finishes, and what we'll see is, and one of them finally win, and the game contract pays off. All right, so the game contract pays off. Okay, so this is how bad a on-chain smart contract can be, or even if you were just implementing as something as simple as a game, as like a chess deal game. Now, what happens if you implement the same exact logic, but with cChannel, or with cChannel's generalized cChannel capability? It looks something like this. Well, first of all, let's go with a simple version. I will make it fancy a little more fancy later. Let's say we still deploy this like a chess game contract. But this chess game contract is a little bit different than the previous chess game contract. It can accept, just like the payment channel, it can accept a mutually signed state that is validated by both counterparties among Alice and Bob. Okay? And well, what happens then is that Alice will pay Bob $5 off-chain using, let's say, a payment network. But this payment network is also something special. It's not Lightning payment network, it's Celer's payment network. And this payment network has the capability to carry a special kind of payment called conditional payment. Right? So this is a kind of the key point that I'm trying to deliver here. That is, for generalized state channel, it's all about state conditional dependencies. So okay, so Alice pays Bob like $5. And the condition is that I will only this payment will only become valid if Bob wins the game, and Bob will do the same thing. And so how to implement this? Let me just go this paper here is imagine that you can have a function pointer saying that okay, this payment you will check that function pointer and whether that function pointer is returns true or not. It's something as simple as that, right? So in that contract, in that smart contract, you will implement some function as a standard interface to accept this kind of checks. Now we can start to see the design pattern for generalized objects, cChannel applications. So if you want to write something that has generalized cChannel capability, you start to need to have these kind of interfaces. First, you need to have an interface to accept a mutually signed state. Now you need to have an interface to start to be able to let all side entities carry some internal state that the outside state is depending on, and so on and so forth. And then, a good thing about this is like, the chance play itself is instant. There's no block propagation needed because they're just passing information between them as well. And this entire process just passes this kind of mutually assigned state. And I also want to just mention one point here that in the middle, what I omitted here is Celer Network infrastructure. Celer Network, if you use Celer Network, it feels like you're using internet. You connect it to it, and you use all these kind of scalable off-chain applications. Okay, let's get a little bit more fancier here. We can actually skip the deployment of this game contract, because this game contract doesn't actually have any state risk. The reason that we need to deploy payment channel contract is because payment channel contract actually is serving the purpose of protecting this money. So it's kind of you're putting your money in a risk condition. How you do this is like basically put that in the contract. But for this kind of off-chain, for this kind of game contract or business logic contract, you don't need to actually deploy it on-chain. You just need to have a way to let it be deployed on-chain whenever needed. So this is something we call a pure off-chain object. There's a blog post that have more detail about this. I won't go into this in detail, but if you guys are interested, we can talk about that in the Q&A session. Okay, and finally, one of them win, and they're still young, right? And one of the conditional payment get dropped, and this is like basically unconditional payment. The conditional payment from bot as automatically become unconditional. Now, I omitted a lot of things here, like how the communication protocol happens, how do you do this kind of state resolution, how do you track each of the state. These things I omitted, but I just want to deliver this key message here, that is how a generalized cChannel works and how a conditional dependency works. Now, the reason I'm omitting those is because the Celer Network SDK handles all of that for you. Okay, so this is more like researchy diagram describing that what we envision as a generalized state channel DF model is a conditional DAG of states, conditional dependency DAG of states. And this is just like an example of that. And for the cChannel, we'll have formal specification and verification capability for this kind of off-chain smart contract. And very importantly, we aim to be designed as blockchain agnostic. So we believe that the off-chain layer is going to be an operating system for blockchain process, right? So it's kind of like a Windows for blockchain. Well, Windows is kind of evil, but so yeah. Okay. All right. Let's see cChannel. Let's take a look at cRoute. cRoute is a provably optimal state routing algorithm. What is the provably optimal state routing algorithm? It has about 20 times the highest performance than the previous state of art. Now, let me talk about what actually payment routing is. This is like a technical slide. So, first of all, why do we need payment routing or generalized routing? Is because it is not possible for everyone to open a channel with everyone else, especially in the context of opening payment channels. And in this generalized channel case, we're opening payment channel with the capability to do this kind of a conditional payment, multiple conditional payment. But it's still, in the end, it's still a payment channel. What does payment channel mean is that I need to deposit money into this to open channels, right? So this is bad because I don't have that much money. So the ideal case for the end user, in our view, is that it's like the internet, right? So you find your service provider, you put all your money with the service provider, and let your service provider worry about connecting to other service providers, and then the whole world, basically. Now, so now we have a network and a channel model. But the problem about that is that, okay, how do you actually find the optimal path to send either conditional or unconditional payment from the source to the destination? Okay? The reason this is hard is because you would imagine this is just a network. We have been having a network for 20 years, but this is surprisingly hard because in the data network world, a link is stateless, right? So what we mean by stateless is that if we take a cable and say this cable is 100 megabits per second, no matter how much data it delivers, it stays 100 megabits per second. But in the state channel world, the link becomes stateful. So let's say we both put $10 into the state channel, and I send you $5. How much money I can send you more is only $5. So the capacity or the capability to deliver payment in either direction is an aggregated result of the past delivery event. That is what we mean by stateful. Now, statefulness become a very big pinpoint in the state routing algorithm because no one has ever studied that in the networking community because there was no such kind of model. So let me just take a very simple example here. This is like very simple network, and D send A $10, the balance changes. A send C $5 via B, balance change again, and B send D $5. Which path to take? Well, for the principle of data networking, it's shortest path is the golden rule, and this is what people have been using also for payment network as well, right? So okay, B send D $5. Okay, shortest path. But if we take a step back and look at this kind of network, we are seeing a very unbalanced network. And this is going to be a huge problem for this kind of a payment channel network because essentially the link from D to A no longer exists. There's no possibility that D can carry any payment to A, right? So why is this bad? Because we still want to have a distributed routing algorithm running in this network. And from I myself have been working in the economic industry and research community for a very long time. And the general principle there is that if you have a distributed routing algorithm, you better have a stable topology. If your topology keeps changing, your entire route map keep churning, keep reconverging, and eventually it collapses. The performance just collapses, flatlines, dead. Okay, so this is bad. Now, intuitively, what's good here is that we just take this path. Like maybe it's a longer path, but it kind of recover the balance between A and D a little bit. So we still have more balance to use later on. Now, this has been the intuition in the community since 2015, but no one have actually developed this kind of algorithm to do this. And we have done some research on that. And we proposed the cRoute, which is the distributed balanced routing, which I'm not going to go into very much detail here. I'm just going to basically throw out the challenge here, and because this is like a very massive mathematical theoretical result. Okay, so just a visual here that this is a randomly generated payment network topology with a cRoute being run with like a randomly generated payment arrival process also, and this is the same thing with the shortest path routing being run. And we can see the huge difference here. That is basically the cRoute is having a very bright future. The shortest path routing has a very bright future. So, okay, so this is just some graph. Okay, COS. Now we talked about the underlying construct of what is the fundamental thing we need to build for these kind of off-chain state channel applications, and we talked about what is the performance core that we need to ensure a high performance network. Now we talk about we finally reached the user and developer. Okay, we finally moved to the top of the stack, COS. COS is a developer framework for CS. It's very abstract. What does that mean? So one key point for any off-chain development is how do you write an off-chain application, right? So how do you fill in the different pieces and stuff that we need, and does the developer need to track all these states? The developer need to track all these state changes and do this kind of state resolutions? This is what COS is for. And there are many interesting points in there, but I just want to pick one particular thing to talk about, which is what we call union identity. So imagine that let's say we're writing a tester again, right? So we have the on-chain Solidity version of the chess running. That's great. But since we're taking most of the logic off-chain, we're taking it away from the blockchain. Where do we write, like, let's say I'm playing a chess on my iPhone. So do we need to write Swift code? If I'm using Android, do we need to write Java code that mirrors the exact same logic of Solidity code? Now, if we have to do that, that's going to be a disaster. Because, we would have to ensure that two sets of code implemented in different kind of languages having the exact same logic, and they can have the exact same interface to bridge each other, which is really a horrible idea. So what we are aiming for is to create this VM native bridge so that you can run EVM and access mobile phone resources on these VMs as well. So this is like a thing that is very cool that we are working on. It is still very much a work in progress, but it's possible to be done because there are similar concepts implemented on mobile already, something called React Native, if some of you guys are familiar with. Okay, so this is like a little bit marketing-ish, but that's also our vision. That is, if how you're using COS is kind of like a user console or your entry point to the blockchain world, where once you install it, there will be multiple different applications that can be run on top of that. That's our vision for the COS. Now there are a lot of things that mobile, especially on the mobile side. Apple doesn't like people running applications inside of applications. So there are a lot of things we need to do to work around that. Okay. We have the MAP demo here. Let's see if it plays. Yeah, this is like a Gomoko game. So this is a traditional Chinese board game, and you can see there's like no delay in block confirmation time. Okay, I will skip that. All right, so let me just take a little bit of time because I think I'm running out of time here.
You're fine.
Yeah, I'm fine. Okay, thanks. So talk about another whole separate aspect for this kind of technology stack, which is the economics aspect. It has been very natural for us to say that, okay, for blockchain, the consensus provide incentive and just get some nodes to run your mining and stuff. It's very natural to think about the incentive in that way. But for many other projects, if you ask, what does your token do? Right. So many of the answer will be, okay, it's a platform currency. But what we are shooting for is a principle of crypto economics. That is, the token has to serve a purpose other than a platform currency. It should have an integral function in this platform and solve the incentive problem that exists in this platform. Okay, so what are the so this is like a three-component economic construct. One is called liquidity backing option, proof of liquidity mining, and a network. Just very briefly talk through that. Now, the purpose of this kind of a crypto economic construct is to solve two challenges. One is liquidity, scalability versus the liquidity challenge. The other is scalability versus the availability challenge. So for off-chain world, we are getting scalability. This is great, but there is no free lunch. We're making some trade-offs as well. What's the trade-off? First thing is liquidity. So what's the network liquidity problem? Remember what I mentioned that this is kind of like a user and service provider model. For user to connect to the network is totally fine because they just need to deposit money with a service provider and be done with it. But being a service provider is actually a very hard job because the service provider needs to have a lot of outgoing deposit to these end users to be able to run as a service provider. Now, the problem is that there are many engineering capable or people that can run these kind of service provider, but they don't have the money. And there are a lot of idle liquidity in this ecosystem, but they don't have the engineer power or the business interest to run them. Okay, so there's a mismatch. The mismatch will cause slow adoption for this kind of off-chain world, and eventually cause centralization, where basically only very rich exchanges with a strong liquidity and also technical capability can run this. We all know how bad the internet service is here. It's poor service, expensive service, no neutrality, and it's closed system. All these things will start to come up again. It's very long-term vision, but it will happen if we don't do something about it. Okay, so we use two components. One is called liquidity backing auction, another is proof of liquidity commitment mining to incentivize a abundant and stable liquidity pool so that these off-chain service provider can tap into whenever needed. Okay, so that's the first purpose of our system. And the liquidity backing auction is really crowdsourcing liquidity. Let the off-chain service provider be able to borrow liquidity from the crowd with relatively low overhead, and it also in the same process reward the previously committed liquidity backers and still ensure 100% safety of the fund for the end users. Okay. Okay. So for this part I won't go into the very detail of each of the mechanisms, but let me just give a very high-level overview. So the proof of liquidity commitment mining is something like this. It's a way you get Celer token. Okay? How do you get Celer token? Is you commit your liquidity into a small black box, and you say, okay, my liquidity is going to be locked in Celer Network for, let's say, 3 months, and it's going to not going to move. I'm committing to that. Once you commit, there's no way you can extract it. And a lot of people is going to commit this liquidity, and this kind of a small black box is becoming your virtual mining machine. Right, so you're essentially mining Celer via your liquidity commitment, what we call it proof of liquidity commitment, right? And the newly generated Celer token will be distributed proportionally to these liquidity commitment miners, essentially. Now, you may ask, okay, why do I want to like basically do this kind of stupid stuff that I'm spending my opportunity cost in this? Right? Why do I want to get a Celer token? What's the use of the Celer token? Well, the Celer token has two purposes. One is in something called the liquidity backing auction. What the liquidity backing auction does is, for this off-chain service provider who needs liquidity as outgoing deposit, they can open a liquidity backing auction. Basically, it's a crowdsourcing contract, saying that I need, let's say, 100 Ether for 30 days, and my upper bound of interest rate acceptable is 1%. Who is going to lend me this liquidity? Okay, open. And these liquidity backers who have spare liquidity to lend will just join these kind of auctions, right? So basically, okay, I'm willing to back you 100 ETH, someone is willing to back 100 ETH and stuff like that. So the tricky thing here is, okay, what if both there are two people all backing 100 ETH to this this liquidity backing auction contract with similar interest rates asked, with same interest rates asked. So who gets to win this auction? Well, here comes the first use of the Celer token, which is determining the priority between similar bid bidders. So this is like a minor use case, but it's also a use case. It's a pretty strong use case as well. That the more Celer tokens we have, are you willing to stake into this liquidity backing auction process? The higher priority you get. It's like an airline frequent flyer mileage program, where you get this kind of an airline frequent flyer mileage when you're helping the network to maintain a stable and abundant liquidity pool. And later on, the system rewarded you incentive compatibly, via adding your priority in this kind of interest backing process. Okay? Okay, I will skip this part. So there are like a lot of the security implication of this, and how do we solve that? I will just skip that part a little bit. So it's also a second score auction to ensure truthfulness of the bids, and how exactly the mechanism is done. And there are two modes. One is like a trust-based, another is more trust-free. But there are various options you can not, things you can tune in the liquidity backing auction process. Now let me get to the second part of the challenge, which is the scalability versus availability challenge. Now we're bringing most of the transactions, or most of the say off-chain, but off-chain comes with the cost. That is, it assumes everyone has to be online all the time. Let's say I and my counterparty has a channel, but I go offline. My counterparty becomes malicious. My counterparty can try to settle a state that is older but seemingly valid when offline. So how to protect that? That is basically I'm not available, but my counterparty becomes malicious. Okay, so this is like basically the problem. So monitoring service is actually considered bad because it's a trust-based monitoring service. It defeats the purpose of decentralization. If we introduce this monitoring service in the system, all these efforts we have done, collapse. Why don't we just like use the trust-based service altogether? And really, there's no security guarantee and very strong economic incentive to collude. Of course, we can build something that is trust-free. After all, we're using blockchains. Okay, so what is a trust-free monitoring service is that you negotiate with the monitor and say, okay, I have like about $10 at stake in this channel, and I'm going offline. Can you also put down $10, and monitor this state for me? And later when I go online, if you haven't done your job well, like the counterparty is becoming malicious and disputed the state, I will submit a proof that it didn't work and get your $10 from you. Right? So this is like possible to implement in a trust-free way, but it's also bad because it first of all requires significant liquidity lockup for the monitoring services as well. Therefore, it doubles overall liquidity lockup for this kind of state channel network, and it has very complex on-chain and off-chain interactions. Like basically, if you're letting the monitor guard your state into complicated interaction back and forth. And it gives you a very expensive and rigid insurance model. It's really negotiated, peer-to-peer saying that, okay, I will get like X% of insurance for Y price. As long as X is not 100%, there's always an incentive for the monitoring service to collude with your counterparty, because your counterparty can become malicious. So how do we solve that? We solve that via something called State Guardian Network. Okay, this slide is too marketing, but yeah. Okay, State Guardian Network is a continuous state pruning sidechain. It's a special kind of sidechain. It consists of state guardians and their Celer token stake. You stake your Celer token into the State Guardian Network to become a state guardian. So in this case, Celer token becomes a work authorization token. You have it, so you can do the work and you can pay it. Now, when the user goes offline, what the user will do is that user will submit the state, their most current state, to the State Guardian Network. And the State Guardian Network will report that, and of course, just like any sidechain, also commit the current like log instead of transactions, it's going to be state, and say it will have like organized hash with other root chain, of course, the end users will have a fee attached to the State Guardian request, and the more Celer token you stake in the State Guardian network, the more likely you get randomly chosen as the State Guardian for this particular state, and therefore the higher income you overall get. So that's kind of like the work authorization or the work authorization token model comes in here, and it's first of all we introduce some anti-collusion mechanism. Where you always have a group of randomly selected state guardian guarding for your state. And each one will randomly have like a designated dispute slot. If let's say the first guy didn't do his job, the second guy does, and the second guy will take the first guy's payment as well as the Celer token is staked on. And another another interesting thing that it's also a very efficient price discovery mechanism. That is how much Celer token is guarded for you, or how many state guardians is guarding for the state is determined by the amount of fee or amount of income flow you're generating for this network. So basically, let's say you're saying that, okay, I'm paying the state guardian network $1 per hour for guarding my state, and this entire state guardian network is receiving $10 per hour. Then roughly about 10% of the state guardians are guarding your state at this particular moment we're submitting the guarding request. And it's also a very, very new kind of a game strategical model. It enables kind of new insurance model that it's not that the state guardian is committing liquidity, but the state guardian is essentially staking future income flows for you, right? And therefore, you are insured with future income flow instead of a spot payment. So if all the state guardians who are responsible for your state didn't perform their job, and later on you find that out, and you can basically dispute in this kind of special side-chain smart contract, and you get all of their Celer token, and therefore you get a income flow, effectively. Ignoring the frictions, you get income flow. So essentially, when you're submitting your state to the state guardian network, there's no negotiation needed to say, okay, what is the potential loss that I have with your state guardian? It's entirely end user's choice to say, okay, I will just tune the amount of fee so that the income flow I generated for the Celer network, for the state guardian network, is creating enough coverage so that if bad things happen, I get these Celer tokens back, and ignoring the friction, I can recover my loss in a certain period of time. So that is the state guardian's incentive model to solve this scalability versus availability trade-off in off-chain mechanisms. Okay, I forgot I have this slide. Otherwise, I should have switch this. So it's simple interaction model, and it's also just an additional note is compact. It's compact sidechain because every state guardian comes with a timeout. When the timeout hits, the entire state guardian network is from the state, and they no longer need to refer the state anymore. So it's not going to cause state explosion as well. Okay, so that's just a quick introduction of the Celer network and what the things we're working on. And we are learning, and we have a couple of engineers leads also here today. After the event, feel free to talk to me or talk to our engineer leads if you guys are interested in learning more generally, and also maybe potentially looking for stuff. All right, thank you.